Welcome to section 5.4, day 1 of AP Calculus, and today we're doing the fundamental theorem of calculus. There are two parts to this theorem, and we also affectionately call it the FTC. So this FTC tells us, and it's in two parts, so this is part 1, tells us that the definite integral of a continuous function is the differentiable function of its upper limit. This is a little bit easier to see if we just do the problem, but basically the fundamental theorem says if you take the derivative of an integral, you are doing two inverse functions, and therefore they cancel each other out. So taking the derivative of an integral with respect to t and going from a constant, which is a, up to a variable, like x, all you do is plug in the variable into the function. So, taking the derivative of the integral of cosine of t is just equal to the cosine of x. That's the derivative with respect to x. The same simple process holds true in example B. We take the derivative with respect to x, and all we do is plug our x into our function. So we have x squared plus x. Sounds too simple, right? Well, it is. And if we do this where we have a few different things happening, you have to account for those. So this example actually goes backwards. Remember our properties of integration. We want it to go from a constant to a variable, so we're going to switch this function around. Y equals negative the integral of 6 to x, 5t cosine of t, and then let's apply the fundamental theorem. So the fundamental theorem here just means that we take the derivative of both sides, and that equals negative 5x cosine of x. You just take this x and plug it in where you see a t. All right, now there is a little bit of a twist. When you are, when your upper limit is a variable that could be differentiated, you're actually going to multiply your answer times the derivative of that variable function. So not too difficult again, dy dx equals, all right, so we're going to take 1 over 5 minus e to the 2x, and actually it's negative 2x. We'll get it right here sometime. Negative 2x, so we also want to multiply this by the derivative of negative 2x, and that's just times the negative 2. So let's clean this up just a teeny bit by putting dy dx equals, put a negative 2 on top, 5 minus e to the negative 2x. And that's your pretty little answer. Moving right along. Oh, here we have one. Sure. This one makes even makes you get even another twist on this whole process. Okay, what we're going to do is be very, very tricky. We are going to use more of our properties of integrals. If we're going from x squared to x to the 4th, remember, in order to apply the fundamental theorem of calculus, we have to go from a constant to a variable. All right, so we are going to take this integral and break it up and go from 0 to x to the 4th, and then subtract 0 to the x squared. So we're taking the area under the curve from 0 to x to the 4th and subtracting 0 to x squared. And that will give us the area in between x squared and x to the 4th. Tricky, huh? Yes, we're always tricky here. So this is ln 2t plus 3. This is a nice little integral too that we need to look at the derivative of. ln of 2t plus 3dt. Okay, so for the first part, what we're going to do is plug in the x to the fourth into our integral, and then we're going to multiply times the derivative of x to the fourth. So maybe it's not as difficult as it looks. Dy dx equals ln square root of 2 times x to the fourth plus 3. And then we need to multiply times the derivative of x to the fourth, which is 4x to the third. Then we're going to subtract the ln of the square root of 2 times x squared plus 3, and then we need to multiply that times the derivative of x squared, which is 2x. Well, that's basically your answer. I mean, we can clean it up a little bit, and I might not clean it up too much. I might put these in front of the ln, this one in front of this ln, just to make it look nicer. But this is basically your answer, so it's not too bad. 4x cubed ln square root of 2x to the fourth plus 30 minus 2x. I guess I don't need to say everything that I'm writing, but that's our answer. Cleaned up. Okay, next. Now we're going to construct a function of the form y equals a to the x. I'm sorry, a to the x, the integral of a between a and x of a function plus c, and we want to satisfy these given conditions. All right, so what we have to do to construct a function that looks like this is, first of all, we need to get y equals. So we're going to take the antiderivative of both sides. When we do this side, we get a y. When we do this side, we're going to plug a t into this equation, use t as our variable. So we have a to x of cosine of t dt plus c. All right, so we've taken the antiderivative of both sides and we've added a c on here. So what we're going to do is make our a equal to the value of x. So let me rewrite it. No. We're going to take y equals the integral of 2 to x. Okay, so what we want to know is, if x equals 2, how can we make y equal to 0? So here, if x equals 2, then this entire integral is going from 2 to 2. Therefore, it equals nothing. The area under the curve between 2 and 2 is nothing. And therefore, in order to make y equal to 0, c has to also be 0, right? So to construct this function where y equals 0, you get 2 to x cosine of t dt, and you don't add anything to it at all. It just looks like this. Because if x equals 2, y will equal 0. Okay, so make sure that you adhere once you get this final answer and you think you're correct. Make sure you try again your x and y and make sure they work in your equation. Okay, let's do that again, because I know this is just a little bit funky. But what you do is you take the x value and put it in for a, and then use the x value again for x. So let's go try it again. This part is not too bad. Taking the integral of both sides, right? You get y equal the integral. We're going to put in ln, we're going to put in t's, ln of t dt plus c. All right, so we're going to use our x value for a, for the bottom number, 5. We're going to put an x on the top, so do this for each procedure. Okay, and then what we're going to do is say, how can we make y equal to 2? How can we make y equal to 2? Well, we're going to try x equals 5, which is what x has to equal. X has to equal 5. So when you go from 5 to 5, the area under here is 0. Therefore, in order to make y equal to 2, our c is going to have to be 2, right? So in this case, if x is 5, c has to be 2. Therefore, our final function must look like this. Y equals 5 to x ln of t dt plus 2. All right, so it looks like to me, in summary, you put your x value in here for A, you put your y value in here for C, and it looks like you are pretty golden. Okay? All right, I think we have one more little part here, which is the fundamental theorem of calculus part 2. This says that the definite integral of a continuous function from a to b can be found by taking f of b minus f of a. And f is the antiderivative. So what you have to do here is take the antiderivative, plug in the upper limit, subtract the antiderivative in the lower limit, and this is how we calculate antiderivatives or integrals. All right, this is a big deal, a very big deal. Okay, so we are going, and by the way, you can always check your answers on these because we have this function on our calculator. But I need to see the work on these when we do them because this is important. First of all, we're going to do the example A, and then we have another example also. Square root of x minus 1 over square root. So before I get started, I am going to simplify this by taking square root of x over square root of x minus 1 over the square root of x. So let's rewrite this crazy little thing, make it a lot easier. 1 to 9. So this is equal to 1 minus x to the negative 1/2 dx. Okay, so this is my function, just rewritten, but it's going to be a lot easier to take the antiderivative out because we can just use the power rule for this. All right, so the integral, in fact, no, let's take the antiderivative or the integral. 1 is x. The antiderivative of x to the negative 1/2 is we're going to add 1 to the exponent. That gives us a positive 1/2. And we're going to divide by that 1/2, that new number. Okay, so add 1 and then divide by that number. All right, in our new notation that you saw above here, this notation using the big integral, we're going to take this is our big F of x, our antiderivative. We're going to take this from 1 to 9, which means we're going to take that antiderivative at 9 and subtract the antiderivative at 1. All right, so all we do is take 9 and plug it into this function. We get 9 minus square root of 9 over 1/2, which is like, let's multiply that by 2. 2 square roots of 9. And then the antiderivative, when you plug in a 1, you get 1 minus 1 over 1/2, which is just a 2. Okay, and if we do that, this is 2 times 3, which is 6. So we have 3 minus a negative 1, and that equals 4. All right, and remember, you can check these on your calculator by using Math 9. Is that correct? I hope so. Math 9 or Math 8. 8 is derivative, 9 is integral, I believe. All right, let's try this same process here. We're going to find the antiderivative at 5 pi over 6. and subtract the antiderivative at pi over 6. Well, first of all, we've got to know the antiderivative of cosecant squared. Well, because we have memorized all of our antiderivatives, we know that it's negative cotangent x. And we want to take that from pi over 6 to 5 pi over 6. Okay, so when we do that, and remember we're going to take the antiderivative at 5 pi over 6, subtract the antiderivative at pi over 6. Ooh, this is going to take some really smart trigonometric thinking, right? So negative 3 cotangent of 5 pi over 6 minus negative 3 cotangent of pi over 6. Okay. That's going to become a plus. We know that. All right. And if you have negative 3 and cotangent at 5 pi over 6 is negative square root of 3. And this is 3 times the square root of 3, positive square root of 3. So what we end up with is these two go boom, boom. So we have 3 of these plus 3 of these. That means it's 6 square roots of 3. All right, now one way to find this is by using a 30, 60, 90 degree triangle and figuring out pi over 6. All right, so if you have a right triangle and this angle is pi over 6 or 30 degrees, and remember, we always use radians in calc. This angle, tangent is opposite over adjacent. So we want adjacent over opposite. Adjacent over opposite is square root of 3. All right, so we know for this one it's positive. 5 pi over 6 is over here in quadrant 2, where tangents and cotangents are negative. All right, these are a few things you should know. Okay, we're done with lesson 5.4, day 1. This is a really, really big lesson on the fundamental theorem of calculus. I recommend you reading your book in section 5.4 and to reconfirm anything you have seen here. Thank you.